Hello students, let's learn flow of a liquid falling film. So flow of a liquid falling film. Let's consider that a liquid is flowing over a vertical flat plate. Have you seen a rooftop where water is fall in rainy season water is falling and forming a film of liquid of water. So that is a scenario. Such cases are seen across many chemical processes: weighted wall columns, evaporation of liquids, gas absorption in liquids, surface coatings, and so many others. So, this is a flat plate. Consider a flat plate, and water is flowing like this on the plate from one direction. Consider z direction, and it's flowing like this, forming a film over a flat plate. Consider a film forming of distance dA, where a thin film of thickness dA will be really less. I'm showing it in a way it will be visible. This flat plate is having length L and width, that's W. Let's consider the flow of liquid in Z direction having velocity Vz. This flow is not in x and y direction, so the velocity here is considered equals to 0. If I consider this fluid that is flowing over a flat plate is having density rho and viscosity mu, then what will be the force acting on it? So force acting on it is gravity force, right? This flow is because of this flow is because of gravity. So what I'll write, force acting on it is equals to rho g delta x. It's acting on this x plane, so delta x into w l, ywl width and length of the flat plate. So this is my force acting on it, while the shear stress that is acting on it. Now here if I draw a a plane, sorry, if I draw a shell on X plane having delta x, this is delta x, this is x plus delta x, and here at distance x I draw a shell. So what will be my shear stress? Now molecular distribution on the plate will be very less, like this. The molecules will be uh, almost near to each other, while at distance dou it will be greater, right? So molecular distribution is greater at distance or in the on the fin. Here if I see, my shear stress will be tau xz on x plane in z direction at x, right? At x here. Now, and here if I check, my shear stress will be tau xz, it will be negative on x plus delta x. Now if I check the molecular momentum flux, so what will be my molecular momentum flux? W flat will be molecular momentum flux in z direction. So it will be WL, width and length of the flat plate, into tau xz at x minus tau xz at x plus delta x, right? So flow of a liquid falling film. Assumptions that we took: thickness of film of the liquid is dou, and it's very small compared to the length and width of the plate. Now no end effects at z equals to 0 and z equals to L are neglected. Let the density rho and mu is the viscosity of fluid. These are the constants, and unidirectional flow है. Liquid flow is in z direction. Liquid is flowing in z direction only. Therefore, Vz, Vx and Vy is equals to 0. Now, steady state condition, laminar flow. Flow of liquid is due to gravity G, and no convective momentum is considered. Fluid is Newtonian. Applying a momentum balance at shell, we obtain tau xz minus tau xz at x and x plus delta x into WL plus rho g delta x into WL equals to 0. What is this? Rate of molecular momentum in across surface at x, rate of molecular momentum out across surface x plus delta x. and gravity force acting on a fluid in z direction. So WL is common, taking WL out and taking limit x tends to 0, I get tau xz minus tau xz x plus delta x upon plus rho g equals to 0. So by calculus, I am getting an equation d tau xz upon dx equals to, by calculation and taking limit x tends to 0, I am getting this equals to rho g. Now integrating this, what I get, integration tau xz equals to rho g integration dx. Right? Now here tau xz equals to rho gx plus c1. To find value of c1, I'll put boundary conditions. So boundary conditions are, now look at the diagram. Here momentum flux distribution tau xz at x equals to 0, tau xz equals to 0, while at x equals to del tau xz is maximum, right? So I'll put boundary conditions x equals to 0, tau xz equals to 0. Why? Molecular distribution is less here, and at x equals to tau molecular distribution is greater, causing shear stress 0 here and shear stress maximum at d at tau. Putting these values on equation 1, I get 0 equals to rho g into 0 plus c1 gives me value of c1 equals to 0. Putting this c1 equals to 0 on equation 1, what I get, tau xz equals to rho g x. Now this is my equation for the next slide. On previous slide, we got equation tau xz equals to rho gx, right? So this is my equation 2. Now, by Newton's law of viscosity, tau xz equals to minus mu dx dvx dvz upon dx. Putting this on equation 2, what we get, dvz upon dx equals to minus rho gx upon mu. On integration, dvz equals to minus rho gx upon mu into dx, I get vz equals to minus rho gx upon mu into x plus C2. Now to find this value of C2, I'll put a boundary condition. At boundary condition, velocity profile. Now check the velocity profile. At x equals to 0 and at x equals to tau, velocity profile at x equals to tau is 0, right? While on the x equals to here is my plate surface, right? This is my plate surface. So at x equals to 0, velocity is greater. At x equals to tau, at x equals to distance of film, this is my distance of film, I mean film thickness. This is my film thickness. So at distance tau, velocity profile is 0, right? While here velocity is maximum velocity. So when I put x equals to tau here on Vz, what I get, Vz equals to 0. Therefore C2 I get here rho g tau upon mu. So putting this value of C2 on equation this, I get Vz equals to minus rho g x square upon mu plus rho g tau square upon mu. So rho g upon mu is constant, common. So Vz equals to rho g mu tau square minus x square. So what I get my velocity profile if I take tau square constant out upon mu 1 minus x square upon tau square. So this is my velocity profile equation. Velocity profile in z direction. Now here you see it's parabolic. Why it's parabolic? It's giving me this parabolic equation, right? This equation is parabolic. So I am getting a parabolic equation. And hence my velocity profile is parabolic. Now to find maximum velocity, what you do? To find maximum velocity,
find maximum velocity Vmax at z direction, I put x equals to 0, right? So if I put x equals to 0 on velocity profile here, what I get, rho g d square upon mu, right? So this is my velocity, maximum velocity. Here I will get my maximum velocity on the surface of plate. Now to find average velocity, that will be here. To find average velocity, I have equation. That said, velocity, average velocity at z direction equals to volumetric flow rate upon area. Here in the equation, I wrote this. Here it will be 2 while integrating this. So this is my velocity profile in z direction, right? Thank you.